We'll go back to share screen. Suppose it's that one. Is it this one that we're looking at? I'm going to get all these people out of the way. View. Sorry. This view. Okay, does that look good? John, can you see that again? Okay. I'm going to steal.
Yeah, we can see that. Thanks, Ruth.
Okay. So data we've used so far, real-time location data. This is reported through the through citizen scientists who report it through the whale report alert system, the RAS. There's other data we could use, real-time behavioral data. Do they seem to be hunting? Are they traveling? Directional information might come out of that. Real-time environmental data, this oceanographic data, currents, tides, that kind of thing. We've used habitat preference, but pathway information like history patterns, those kinds of data are available through archives. Try to get rid of that. That's probably a better way to do it. Okay, so how do we get to a real-time forecasting system for movement of whales near coastal shipping lanes? One natural approach is to use the state space model, and a state space model is a useful approach because it merges data with models that predict forward in time. And so in the movement context, that forecast would be a movement model. And it also requires an observation model. So it takes into consideration that the data that you observe comes with a certain kind of error. And so with citizen science data, they may not put the whale pod in the right place within a margin of error. And with hydrophone data, of course, there's a whole different kind of envelope of error around when hydrophone detects a whale. And maybe we'll talk about that and some talks later today. So this slide just sort of takes the state space model as one rectangle here, which is the data in. We currently in Marine's paper have visual citizen science data. It takes a movement model, and the movement model we use is a continuous time correlated random walk. Continuous time is important because sightings don't always come in 5-minute regular sequences. And historical data, we integrate density surfaces or occupancy models of where killer whales like to go as a term in the model, and I'll briefly touch on that later. As well as there's a set of parameters that describe how an animal is moving. So is it moving in a directed manner, or is it does the pod seem to be foraging or moving in twisted pathways? And so that the estimation of those parameters are done online, in the sense that they're done when you estimate the state, and in this case the state is where are the animals. So that locational estimate of where pods are is the state in this state space model. So here's a picture of real-time visual data being collected at East Point. And the point of this is to say that this data is very dependent on data. So the model doesn't predict well unless there's data coming into it. So it forecasts forward in time. And if it's been a long time since the last sighting of whales, then the potential coverage of where whales could be gets wider and wider. And so it's really important, and part of what we'd like to do moving forward is not only to have the visual data from citizen science networks, but also to incorporate hydrophone data. Hydrophone data, as everyone knows, should be available 365 days a year, and day and night, if everything works properly. So at the top here, it's supposed to be a set of binoculars. So that's a typical way that we get visual data. There's also drones, not a Longhorn cattle there. There's also overflights that we could incorporate into this model. So we're not fixed on visual data having a particular form. The state space model, can take any form of data that has information about location of whales. There you go. And then, of course, what I think many people in this room are aware of, there's a lot of initiatives moving forward with satellite data. And so again, that's another information about location of whales that we'd like to, in time, could incorporate into this model. But today we wanted to mostly focus on hydrophone data. But before we get there, just briefly go through what the model is. So the movement model is formulated in terms of velocity. And so it's a stochastic ODE, and that's formulated in terms of velocity. So we can discretize the Ornstein equation at the top and discretize it to get whale velocity using whale velocity at the previous time step. Some drift, or what we term in this model as the bias that pulls the animal towards places where it would like to be. And then the behavioral parameters here as a weighted term that balances the velocity at the previous time point and where it would like to go. And of course, we're not interested per se, we don't want the state to be velocity, the state is actually the location. So we just integrate the term for velocity, and we create or we get displacement out of that term. So the point of location at time t is a function of the last location plus the displacement. So that should make some sense, hopefully. Maybe I'll skip over this, but it's just to say this is a data assimilation scheme. So you switch between data into the system, and then you predict forward, and then the data itself corrects that prediction, and then you predict forward in time again. And so the next set of slides here is just a schematic to show how this works. So here, let's say we have a whale pod reported here. The movement model predicts forward where the possible paths would be using that velocity and displacement equation. And so it creates, maybe it's a bit hard to see, but it creates a sort of density surface, a local density surface, or where we expect the whales to be in the next, well, as you move forward in time, it just predicts forward in any increment of time that you're interested in. And then it waits until the next data point is observed. So it's this, you observe a data point, it informs where the possible tracks are from that point forward. And then it waits until another observation is observed. So in more and more observations mean better and better predictions in that local region. And here's just a quick video of that. It goes really fast, but the idea here is we've got a pod moving through the Salish Sea, and it's giving those potential locations and the density, the regional density surface around those locations. So the data itself is what corrects the forecast system to take out those locations where there's no way it got from here to here without passing through a particular subset of those pathways. And so, oops, need to get to the next slide. So I briefly introduced the idea that this model has a drift component in it, and I'll just briefly say that this is a density surface map here with red saying where whales are more likely to be observed, and this is a work that Joe Watson did for his PhD. And we use this as the drift function. So it pulls the killer whales towards areas where it's more, where they're more likely, or southern residents where they're more likely to be found. And as one might expect, this first part of the forecast time horizon, we have data. You can see that the errors around those forecasts are relatively small. And once we stop ingesting data, the error around those projections gets bigger and bigger. And so we, in the example that we published, we can get up to about 2.5 hours of forecasting. I wouldn't say accuracy, but 2.5 hours. We're still within the window where we're capturing the killer whale movement. And so with hydrophone data, we're really hoping that we can improve on that. And so where to next? Hydrophone data. So the first one, more abundant data, hydrophone data is where we're focusing for the next few years. There's other forms of data that are around that we haven't yet used, and I touched on them earlier. So currents, tide, season, prey fields would be great, although I'm not sure we can get to prey fields, but anything that whales are using to make decisions about where they voluntarily move. And then historical whale tracks. So data mining is something that we've just started as well with some of the whale museum folks over in San Juan Island. Outputs from Salish Seacast or the Live Ocean. These are sources of information about things that we might not think would be useful or predictive necessarily of movement, but they may be proxies for something that killer whales are using to make decisions about where they go. So this is a subset of them. We've got salinity, temperature, zooplankton, possibly areas of productivity might be represented in these variables. So we'll be trying to use these variables as well. And these are available in real time, as also with predictions forward in time. So these oceanographic models that output these fields also use forecasting framework. And what we're going to be talking about today is some of the challenges of hydrophone data, using hydrophone data. So on the diagonal of this confusion matrix here, we're doing really well. And on the off diagonal, we're making errors. And so there's different ways these kinds of errors enter into detections of killer whales. So just looking at this top line here, where we've got a southern resident present, in reality, the whale is there. True positive indicates that you're detecting that whale, given it's there. A false negative there is that the killer whale is there in reality, but you're not detecting it. And so one of the challenges that I know DFO has addressed is trying to understand that envelope around a southern resident killer whale. So here I've just got a schematic of imaginary zone 1, 2, and 3. Zone 1, your detection is likely. Southern resident killer whales don't always vocalize, so it's not equal to 1, but there's some higher detection probability. In zone 2, you may detect them. They may be facing the wrong way. There's a whole set of reasons why you might not detect them. And in zone 3, the probability of detection is 0. Whales are too far away, or whales are behind land. But the whales are still in the vicinity of the hydrophone. So these are challenges that we'll be focusing on, and other people will be addressing in their work as well. So where are we going from here? We've got hopefully going to be focusing on trying to before we get to building this in a way that we can use it as an operational system. That's the word I was looking for. We need to integrate hydrophones and see how that works in archive mode. So we'll be building models and ways to check that this is actually reasonably good at forecasting where whales are going. It's not just about southern resident killer whales. There's a number of other species at risk. We started with southern resident killer whales, but we intend to work with the transients, with humpbacks, and then at the entrance to Juan de Fuca, gray whales potentially and other species at risk out there. Historical whale tracks and habitat occupancy models, those will be a focus as we move forward, not just for southern resident killer whales, but other species of whales. And then hopefully we'll get some new hydrophone placements as well to try and fill in the gaps. So we have a more complete picture of where whales are 24/7. And so